a new type of spin orbit torque,
Okay.
or SOT for short, that could completely change how we design electronics in the future.
Yeah.
Imagine data centers that only use a fraction of the energy
Wow.
that they do now.
Yeah.
That's the potential we're talking about here.
That's right. To really understand how this all works,
Yeah.
we first need to kind of get back to the basics of spintronics.
Okay.
Instead of just using the charge of electrons,
Right.
like in conventional electronics, spintronics leverages the intrinsic spin of electrons to store and process information.
So we're going beyond just using electrons as like
Yeah.
tiny packets of charge.
Yeah.
We're tapping into their spin, which acts like a tiny magnet
Exactly.
to do some really cool things.
Exactly. And the key players in this game are these tiny structures called magnetic tunnel junctions.
Wow.
Or MTJs for short.
MTJs?
These MTJs are the building blocks for things like MRAM,
Okay.
a type of memory that's poised to become much more common in the future.
So I think I get it. These MTJs are essentially tiny switches
Yeah.
controlled by magnetism. And this new SUT
Right.
is how we can flip those switches even more efficiently.
You got it. And to make those switches even more effective,
Okay.
we use materials with perpendicular magnetic anisotropy, or PMA.
PMA?
In these materials, the magnetization wants to point either up or down,
Okay.
which is perfect for packing more data into a smaller space.
Okay, so PMA is like building upwards in a city to make the most of the available land.
Yeah.
So why don't we just use PMA magnets everywhere?
Right.
There's got to be a catch, right?
And of course, manipulating these PMA magnets has traditionally required an external magnetic field,
Oh.
which adds complexity and uses more energy.
Yeah.
That's where our star of the show,
Okay.
unconventional SUT.
All right, let's talk about unconventional SI. What makes it so unique?
What's really exciting is that unconventional SO uses spin currents that are polarized out of plane.
Okay.
Think of it like this. Imagine a helicopter.
Okay.
It can move in any direction while its blades,
Yeah.
which we can think of as representing the spin,
Uh-huh.
are also rotating in a specific direction.
So in conventional SO, the spin and the current flow are like a car, always moving forward.
Yeah.
But with unconventional SO, we're like a helicopter,
Yeah.
able to move and spin in any direction.
A perfect analogy. This allows us to control the magnetization of PMA magnets much more directly
Wow.
and efficiently than with traditional methods.
This is starting to sound incredible.
It is.
So what are the practical implications of this unconventional SO?
Well, for starters, it could revolutionize memory technology.
Okay.
MRAM, which relies on these MTJs,
Right?
could become much faster, denser,
Wow. Okay.
and use significantly less power.
And if we can make memory more efficient,
Yeah.
that means our phones, our laptops, and even those massive data centers
Right.
could operate with far less energy.
Mm-hmm.
That's a huge win for both our wallets and the environment.
Absolutely, but the applications go far beyond just memory.
Oh, wow.
Unconventional SOT could also be used to create more efficient logic devices,
Okay.
which are the brains of our computers.
So we could be talking about a fundamental shift
Yeah.
in how we design and build electronics.
Precisely. And while the theory behind unconventional SOT is exciting,
Yeah.
applying it to real-world materials presents a unique set of challenges.
Uh-oh, I'm sensing a butt coming.
Well, the theory works beautifully when we assume a perfect crystal structure.
Okay.
But in reality, most materials we work with are polycrystalline,
Okay.
meaning they're made up of lots of tiny crystals or grains all jumbled together.
Ah, so it's not just about the material itself, but how it's arranged at the microscopic level.
That's right.
I imagine that makes things a bit tricky.
It does. These grains can have different orientations.
Okay.
And that affects how efficiently the spin currents can flow. If they're not aligned correctly,
Yeah.
they can actually cancel each other out,
Oh, no.
reducing the overall efficiency of unconventional SUT.
So it sounds like a logistical nightmare. How are researchers tackling this challenge?
They're getting pretty creative. Scientists are using techniques like ion beam assisted deposition, or IBAD for short, to nudge those tiny grains into a more favorable alignment during the fabrication process.
So it's like we're not just building with these materials.
Right.
We're sculpting them at the atomic level.
Yeah, it is. And there's another technique called off-axis sputtering,
Okay.
which involves depositing the material onto a surface at an angle to encourage the grains to align in a specific direction.
I'm picturing it like spray painting a fence at an angle
Oh, exactly.
to get a more even coat.
By controlling the deposition process with these techniques, researchers are getting closer to creating materials that are perfectly tuned for unconventional SOT.
It sounds like a lot of trial and error. Are there any success stories to celebrate?
Absolutely. There's been some exciting research focusing on a material called Mn3 GaN.
Mn3 GaN.
It has a really unique combination of properties that make it ideal for unconventional SOT.
So Mn3 GaN is our poster child for this new technology.
You could say that.
What makes it so special?
Mn3 GaN has a low crystal symmetry,
Okay.
which allows it to generate those out-of-plane polarized spin currents that are so crucial for unconventional SOT.
Yeah.
And what's even more is that it's relatively easy to work with.
Oh, wow.
Making it a great material for researchers to explore and refine this technology.
Okay, so we have a promising material and some clever techniques for controlling its structure.
Mm-hmm.
What have scientists learned so far from studying Mn3 GaN?
There have been some fascinating findings. One key takeaway is that achieving perfect alignment of those tiny crystals might not be absolutely necessary.
Really?
Even with a bit of randomness, Mn3 GaN can still exhibit significant unconventional SOT.
That's encouraging. It sounds like we don't need to be obsessive about getting every single atom in the perfect spot.
That's right, but controlling the out-of-plane texture, meaning how the grains are oriented perpendicular to the material's surface, is particularly important for maximizing efficiency. Remember, those out-of-plane spin currents are the key to unconventional SOT.
It's all about making sure those tiny helicopters are pointing in the right direction.
Exactly, and the research on Mn3 GaN has shown that techniques like IBAD can be very effective in manipulating that out-of-plane texture.
So we're not just theorizing about this technology. We're actually seeing tangible progress in the lab.
That's the exciting part, and this progress is happening quickly.
Yeah.
It's amazing to witness how rapidly the field of spintronics is advancing.
It makes me wonder what other breakthroughs are just around the corner. But before we get too lost in the future, let's touch on the practical side of things.
Sure.
If unconventional SRT is so promising, why isn't it already being used in our everyday gadgets?
Well, there are a few hurdles we need to clear before this technology becomes mainstream. One of the biggest is scalability. Most of the research is still happening at a small scale in labs, figuring out how to manufacture these materials and devices reliably and cost-effectively is a big challenge.
So it's one thing to bake a perfect cupcake, but quite another to mass-produce 1,000 perfectly identical cupcakes.
A delicious analogy. Ensuring consistency and reliability is crucial if we want unconventional SOT to be adopted on a large scale.
I can see that. No one wants a phone that only works half the time. Are there any other challenges on the road ahead?
Another challenge is integration. Figuring out how to seamlessly incorporate these new materials and devices into our current electronic systems isn't always straightforward. There are many different components that need to work together in harmony.
It's like trying to add a new wing to a house.
Yeah.
You need to make sure it complements the existing structure. And doesn't compromise its integrity.
Exactly. It's a complex puzzle that will require collaboration between materials scientists, electrical engineers, and computer scientists, to name a few.
Wow.
But I'm confident that with continued research and innovation, we'll overcome these challenges.
I'm excited to see what the future holds. It's like we're on the verge of a new technological era.
It is.
And unconventional SO is one of the keys to unlocking its potential.
I think so.
It's a future where our electronics could become vastly more powerful and energy efficient.
Yeah.
Which has implications not just for our personal devices, but for large-scale computing data storage. And even the way we approach artificial intelligence.
It really does.
It's almost like we're talking about science fiction becoming reality. But speaking of reality, let's address something that might be on our listeners' mind. With all this talk about manipulating materials at the atomic level, are there any ethical considerations we need to keep in mind?
That's a great question, and one that's becoming increasingly important as we delve deeper into nanotechnology. The potential benefits of these technologies are enormous, but it's crucial to consider the potential risks as well.
So it's not just about what we can do, but what we should do.
Exactly. We need to be mindful of the potential environmental impact of these new materials and manufacturing processes. And as with any powerful technology, there are always concerns about potential misuse. Open dialogue and careful consideration of these issues are essential as we move forward.
It's a reminder that scientific progress should always go hand in hand.
Absolutely.
With ethical responsibility.
It should.
We need to ensure that these technologies are developed and used in ways that benefit humanity as a whole.
Absolutely. And that requires a collaborative effort between the scientists, policymakers, and the public. Open communication and careful consideration of these issues are crucial to ensure that we're steering this technological ship in the right direction.
It sounds like we're entering a new era of scientific exploration.
I think so.
Where the possibilities are almost limitless.
Yeah.
But let's not get ahead of ourselves.
Yeah.
Before we see unconventional SOT in action.
Right.
What are the next steps for researchers? What mysteries are they still trying to unravel?
Well, one area of active research is exploring new materials with even better properties for unconventional SOT. M3 band has shown great promise.
Yeah.
But there might be other materials out there that could be even more efficient or easier to manufacture.
So the hunt for the perfect spintronic material is still on. What qualities are they looking for?
Researchers are looking for materials with a very unique combination of properties. They need to have the right crystal symmetry to generate those out-of-plane spin currents. But they also need to be compatible with existing manufacturing techniques.
Yeah.
And ideally, they should be readily available.
And
environmentally friendly.
It's like searching for a needle in a haystack.
Right.
But the needle is made of multiple materials.
Yeah.
Each with its own specific properties.
A very apt analogy. And beyond the material itself, scientists are also working on refining those fabrication techniques we talked about earlier, like IBAD and off-axis sputtering.
Right.
The goal is to achieve even greater control over the texture of these materials, maximizing the efficiency of unconventional SOT.
So it's a two-pronged approach, finding the best materials and perfecting the methods for shaping them.
That's right.
What about the actual devices themselves?
Yeah.
How will unconventional SOT be integrated into the electronics of the future?
That's where things get really interesting. Researchers are exploring a variety of device architectures that could harness the power of unconventional SOT. One promising avenue is something called spin-orbit torque RAM, or SOT-RAM.
SOT-RAM, it sounds like the next generation of memory technology.
Yeah.
How does it differ from the MRAM we use today?
So, current MRAM technology relies on a phenomenon called spin transfer torque, which requires passing a large electrical current through the device.
Yeah.
This can lead to energy consumption and heat issues.
Right.
SOT-RAM, on the other hand, uses spin currents generated by the spin Hall effect, which requires significantly less energy.
Oh, so it's a more energy-efficient way to flip those tiny magnetic switches in RAM.
Precisely, and that translates to faster, denser, and more power-efficient memory.
Wow.
Imagine smartphones that can store terabytes of data while barely sipping on battery power.
Sign me up for one of those. But memory is just one piece of the puzzle.
Right.
What about the logic devices, the brains of our computers?
Yeah.
Could unconventional SOT play a role there as well?
Absolutely. There's a lot of excitement around using unconventional SOT-O to create novel logic devices that are far more efficient than our current transistor-based technology.
So we could be talking about a fundamental shift in how we approach computing itself.
Potentially, yes. Some researchers believe that unconventional AXOT could pave the way for a new paradigm of computing. One that's inherently faster, more energy efficient, and perhaps even capable of mimicking the way our brains process information.
Now, that's a future I'd love to see, but for now, I think we've covered a lot of ground.
We have.
What's one key takeaway you'd like our listener to remember from this deep dive into unconventional AXOT?
I think the most important takeaway is that we're on the cusp of a major technological revolution.
Wow.
Unconventional AXOT has the potential to transform the way we design and build electronics, leading to devices that are faster, smaller, more powerful, and far more energy efficient.
It's a reminder that even in a world that often feels dominated by incremental advancements, there's still groundbreaking discoveries waiting to be made. Discoveries that could change the course of history.
And often those discoveries come from exploring the seemingly esoteric realms of fundamental physics, like the spin of an electron. Who would have thought that something so tiny could hold the key to such profound technological advancements?
It's a testament to the power of human curiosity.
It is.
And our insatiable drive to understand the universe around us.
I agree.
And who knows what other mysteries are out there waiting to be unraveled.
So many.
Perhaps one of our listeners will be inspired to dive deeper into the world of Spintronics and make the next big breakthrough. Thanks for joining us on this deep dive. Until next time, keep exploring.